So for our first example, we have that a car dealer says the mean price of used cars sold in the last year is at least $21,000. You suspect this is inaccurate and find that a random sample of 14 used cars sold in the last year had a mean price of $19,189 with a standard deviation of $29.50. Is there enough evidence to reject the dealer's claim at alpha equals 5%, assuming that the population is normally distributed? So again, just like before, first step when we're verifying these conditions, we have normal distribution, we have a given population mean we're going to be working from 21,000. We have that sample of 19,189 with a standard deviation of 29.50. So we have all the pieces we want to work with. And in particular here, something you should pay attention to when you're trying to figure out what way to approach these problems, whether it's a z-test or a t-test or what have you later, is you should notice that when they're talking about that mean and standard deviation in that second part there, they say the mean price of the sample of 14 is 19,189, and the sample standard deviation, they don't specifically say sample, but in that context it should be somewhat clear, is 29.50. That is, the 29.50 specifically corresponds to that sample of 14 cars. It is not a population standard deviation, so we know that we're going to be doing a t-test instead of a z-test because we only have information about the population mean. We don't get anything else. That's kind of the giveaway. Now from there, determining what our hypotheses are, it takes a little bit of subtlety. You have to be a little careful about what information you want. Obviously, what we're looking for there is something in terms of that mean, mu being 21,000, specifically $21,000, but this time I'm not going to write units because, well, why not? But it might not be super obvious based on the statement of this problem whether we're looking for something where they're equal, not equal, what have you, because the way it's stated, it's not as clear as it could be. Here they say that the car dealer says the mean price is at least 21,000. Now, you look at that and you might hear that phrasing in there that they say it's 21,000, you think it's a claim, but then you flip back to what you saw in 7.2 and you remember that usually in the first sentence when they're saying something, there's an implicit bias towards that being the truth. But I guess in this place, we don't trust car dealers. Hopefully after 7.1, we don't have a ton of faith in car dealers, and we're actually treating that at least there as our claim. That is, we are claiming the mean price, the mean cost, as it were, to you is $21,000, where you suspect that it is actually not that. You don't suspect anything in particular about it, you suspect that that's inaccurate, where when we're suspecting at least is inaccurate, we need the opposite, which means we're suspecting that it's smaller. And this indication of being smaller, if you're paying attention, you can get that from the fact that your mean is a little lower. Now, usually you would have that inclination beforehand, and then whether or not the data shakes out that way is a different story, but for the sake of being a good example, it's kind of implied. Anyway, these are our hypotheses where the null is the one that has the potential equality. So the null is our claim here. Again, that doesn't always happen, but it comes up every now and then. And our alternative is what you suspect. It's not really a claim because you're not specifically saying that you claim that is different, that is smaller. You're just thinking maybe it is. So that is our alternative, where from there, if we want to identify our level of significance, as it were, that's the given value here, the standard value, 5%, where in particular, because we are looking for things potentially being smaller, we're looking to the left of that middle mean in the distribution. This is going to be a left-tailed test. And for our next trick, we're going to look at the degrees of freedom in our test statistic. So, degrees of freedom is pretty easy. Still, as we remember from when we first introduced the t-distribution in chapter 6, that's going to be our value n minus 1 here, and the sample size is 14, so 14 minus 1, or 13 degrees of freedom. Another indication usually that we want to use the t-distribution is a small sample size. That's what it was originally designed for, small amounts of things. Then we need our t-score, our test statistic here in terms of the t-distribution, but that still has very much the same formula that we're used to. X bar minus mu over now s divided by root n. Remember, we're dealing with s because it's all we've got, but it still has the same flavor of standard error thing. It's just less information, less options. So we're doing our best here, but a t-score is generally not as good as a z-score. In any case, here that's going to have the flavor 19,189 minus 21,000. I'm trying to write small so I can maybe fit it all on one line, but it's going to be close. Divided by 2950 over the very nasty square root of 14. That's going to be about 4, though, which will give us a t-score that is approximately negative 2.297. So about negative 2.3 standard deviation-ish things below that mean there, which would correspond to a distribution something like so as pictured here, where progressing from that point, we have a couple of different options, but seeing that picture, we can either go forward with a critical value method or a blanking for here p-value method. I'm going to use the p-value method here, and if you want to get that p-value, you can see it there, even though it's maybe a little bit spoiled for you guys if you're paying close attention. You can go ahead and use a tcdf function in your calculator to get that specific value, or what I'd really recommend getting comfortable with, much like the z-test in the last section, we have the t-test in this section for being able to handle these hypothesis tests for the mean without sigma. So you run that test, and what you should get is some flavor of p-value that will come out in the neighborhood of approximately 0.0194, so about 2%, which importantly is less than the value of alpha in this case. Whoa, that's even more of a delta than usual. Let's try that again, even with a smudge. It's better. But importantly, p is less than alpha, p is small, so you might find yourself wondering, do we finish this the same way as before? And yes, the process, once we get around the little bit of computation here that's different, is almost identical. Same flavor of hypotheses, and ultimately, we're making the same flavor of decision. Here, because the p-value is less than alpha, or if you want to think about it in a different way, because the test statistic would land inside the rejection region, thinking in terms of critical values, we would reject the null hypothesis. P is low, you do the thing. And then from there, once we have our decisions, we have all of our pieces, we can actually interpret this where we would say something to the effect of, there is enough evidence to reject the claim that the mean price of used cars sold in the last 12 months is at least $21,000 for level of significance alpha equals 5%. Where again, we were claiming the null hypothesis, and we have rejected the null hypothesis, so we can say that we are rejecting the claim, as it were. Remember that language is picky, it's specific, you just have to be very careful about it, but that's how it would work in this case. We are rejecting the claim, we are rejecting the null hypothesis. So, with this in mind, we're going to get one more example here using the p-value approach that's, I think, a tiny bit lighter, and then we'll get one with critical values as well, just for the sake of completeness.